Good afternoon, everyone. Today, we're going to continue our discussion on the modeling of time series, in particular, making use of the ARIMA or the Box-Jenkins approach. So, quick review of what we did. We created last time an object called AP, and we used the quant mode package, in particular, the get symbols function. These were the parameters that we used. Okay, and I already have that object. So let me just check here. It's here, AP. So it's an XCS object, extensible time series object. And then we said that we're not interested in modeling all the components of that AP object, open, high, low, close, volume, and adjusted. We're just going to make use of the of the adjusted price. So we subsetted AP with we just got the sixth column, which is the adjusted price. Okay, and then we changed the column name to adjusted. So the AP object that I now have here is, let me just show you. Okay, is this one. So the AP object consists of the prices of the Apple stock adjusted prices from this is January 2, 2015 until December 2023, December 2029, December 29, 2023. Okay, so that's our data. Okay, and last time we said that if we plot this object, we can see that this is a non-stationary object, which means that it does not have constant mean and constant variance. Okay. Now, in modeling financial time series, what we're interested in usually is the returns of our data. So what we did was to get the we used the okay, we used return that calculate here. We created this object L APRET because this is just a name. It it's an object containing the log returns of Apple, the adjusted prices of Apple. We use the return that calculate from the performance analytics. You can also use calculate returns here. And the method that we use is log, and then we omitted the first row so that we have no missing value. Okay, if we want the discrete returns, okay, we said that we can make use of the method is equal to discrete. Okay, so here, let me just just use Apple ret here, and then same thing, return that calculate, and then discrete. So if I run this, okay, and by the way, Apple ret will now have a missing value. The first row, this is Apple ret. Let's just double check. It has a missing value. So to delete this missing value, we can just put here in the formula NA dot omit, and then comma true. Okay, so this will now create Apple ret with the missing values removed. Okay, so once again, let me view that. Apple ret. And it contains the discrete returns or the simple returns. And the first row, which was a missing value, has been removed. All right, so I hope you have that, class. So kindly chat, please, if you have that. If you were able to generate already Apple ret, log Apple ret, and of course the Apple data set first. So let me pause for a while and get your feedback if you were able to get those. Although we did this already last time. So I'll wait for you to give me your feedback, please. So waiting for the others. If you have any questions, clarifications, please feel free to ask. Okay, good. So no questions? Okay, thank you for your feedback. All right. So let's have a brief review. Let's just review. I don't think I have shared this with you yet. So let's summarize. Okay, let's see if this will. Okay. So in the chat box, I gave you the summary of the steps in determining the ARIMA model. So what have we done so far? Of course, step one is loading the data, okay, and then doing some descriptive statistics, descriptive analytics about the data, and check the data if it's stationary or not. So what we did last time was the data that we were using is initially it was AppleRet. Cut yung na-send. Bakit cut?
Sir, nag-end siya sa partial A.
Okay.
Nag-deep yung sentence.
Okay, sorry. Okay. All right. Step one, class, download the data, check the data, and check first if it's stationary. So we use quant mode. We downloaded Apple prices. For your case, you're going to use Philippine data. So you have to know how to download data from Refinitiv or from Excel. You're going to use Philippine data, stock prices from the Philippine Stock Exchange. Okay, so if the data is not stationary, okay, we need to do transformation. Okay, so if we were modeling AP, the Apple data set, then we would have definitely, okay, let me put it here. If I plot the AP, this consists of the prices of Apple, the adjusted prices, and definitely this is not stationary because this is this does not display non-constant mean nor constant variance. Maybe constant variance, but we're not really so sure. We have to check that statistically. Okay, but definitely non-constant mean. So if the data is not constant in mean, the simple thing to do here, the best thing to do is, okay, you can see here that this is a trend. The easiest thing to do here is to difference the data. Get the difference of the data. Okay? By differentiating the data, you might be able to create a stationary data series. Now, sometimes there will be two orders of differencing. Sometimes getting the first difference will not cure the non-constancy in mean. But definitely, usually the first differencing will already cure that. But if not, then you may do a second differencing. Okay, so what's a second differencing? So if these are the prices of let me flash that. So you know what second differencing means? If this is Apple red, then the first differencing will be, okay, but nawala. Okay, so this Apple red. The first differencing is, let me illustrate that. So this minus this, right? Because this is the with reference to the current value and the past value. This is current with respect to this one. So you get the difference between these two. Okay, so that's 192 minus 193, you have a figure here. Then 193 minus 192, another figure here, until the the last, and the last will not have a corresponding difference data. So this is your difference one, log one, order one differencing. Now, if you plot this time series and it's not yet constant in mean, then you can do another differencing. Okay, so this is log two differencing now. What's log two differencing? You difference the difference data. Okay, so if this is, let me just approximate it around negative 0.9, for example, this is one, this is 0. Whatever this is, 0.6, for example. Okay, so you have these values here, your difference data. Then your second differencing will be negative 0.9 minus 0.6. Okay, so that's your log 2, okay, order 2 differencing. So that's a different time series. Okay, now take note, when you model this later on, you will have to revert back to your original data. Okay, and we'll discuss that. Okay, so that's how you get the differencing. Let me erase this. And of course, in R, it will simply be diff of diff, right? So you'll have two differencing. So to look at, to apply it here, our apple is not a stationary data. So if you want to use the Box-Jenkins approach to model apple, then you have to create a difference time series. So I'm creating a DAP difference time series, which is just diff of AP. So that's simple. And then I will have to remove the NA.omit. I will have to remove the first value because it's NA, and then this should be true. Okay, so quite straightforward. And then I'll just plot the AP. So if I run this class, then I now have, you notice that with first differencing, I was able to cure the non-constancy in mean. So it removed the trend. So now you have a detrended DETRENDED, a detrended data. This is now a detrended time series where we removed the trending because originally our AP was behaving that way. All right. So is this now stationary? Well, graphically it seems so, but we will have to check via a statistical test. All right. So that's what we did that's to get the difference. Okay. However, if the data was showing some non-constancy in variance, so which means that the data seems to be behaving this way. So this is a this is a data set where the variance is not constant across time. Okay, so this is definitely not stationary also. So how do you cure this scenario where the data is not constant in variance? So one way to do that is to get the log transformation. So getting the log transformation class could remedy this non-stationary invariance. Okay, what we discussed a while ago was non-stationary in mean. Okay, so if it's stationary in mean, for example, the average looks the same. There's no trend. Okay, only non-constants invariance. Then you don't have to get the difference. You just get the log. Now for this one, if our data looks like this, so there seems to be a trend and there's non-constancy invariance, then we will have to remedy both by getting the difference in the log. Now take note, you have to get the log first and then get the difference. Why is that so? Based on what we discussed last time, if you get the difference first, it most probably will generate negative values. And if you then get the log, then that will return an error because you cannot get the log of negative values. So how is it done? Get the log first and then get the difference. Okay? All right. In our case, class, what we did last time was we got the log and then we got the difference. Now, why is that so? We did that because what we really need is to model the returns, the log returns of Apple. Okay. So whether your data was not displaying that, okay, whether your data did not have a trend, nor did it show constancy in non-constancy in variance, we still had to do this because what we have are prices, and we're not interested for now. We're not interested in modeling the prices. What we're interested in is modeling the returns. Okay, let me pause for a while. Is this clear, class? Could you please chat if that discussion is clear to you? Okay, good. How about the others? Okay, thank you. Thank you. All right, so very important yung class ha. Sa case nyo, log returns din yung imamodel nyo. Okay? Log returns then. So you will have to do some transformation. You're forced to. Kasi syempre, pag kinuha nyo yung prices, kahit na walang trend yan, which is might be highly unlikely, or kahit na walang constancy in variance, kahit na constant in variance yan, you still have to get the log returns because that's what you're going to model. Okay, so step five here says that we have to check our data statistically. Okay, if it's if there's stationarity. All right. So what we did last time, class, was yung ginawa natin, ano? Okay. So this was our step 5. Okay, we're using the log AppleRet. Okay, so this is the log returns of Apple. And if we plot this, we know that this is stationary. Okay. However, there are volatility clustering here, which might indicate that we might have difficulty modeling this using ARIMA, but anyway, we'll model it first. And then we have to test statistically. So this is what we did last time. We used the augmented Dickey-Fuller test from the T-series package. Okay, I think I gave this to you last time, but anyway, just to be sure. And then this one, Control C. Okay, let's go back there. The augmented Dickey-Fuller test, okay, if I run this from the T-series package, okay, all right, the alternative hypothesis is that the time series is stationary. Therefore, the null hypothesis is that the time series is not stationary. Okay, and then we have this Dickey-Fuller stat negative 11.905, where the p-value is 0.01. Okay, therefore, since this is less than 0.05, we reject the null hypothesis that the time series is not stationary. So we can now conclude that L AP rep is stationary. Okay. Now there are other tests like this one, class. From the URCA package, this is the unit root test. Okay. Unit root co-integration test. We have this function unit root that Dickey-Fuller, and we're testing whether our log AppleRet. Okay. For the type, there are 3 types: non, drift, and trend. Okay, we don't have time to discuss this, but I would that you, on your own, try to see what's the difference between non, drift, and trend. But these are all tests of non-stationarity. Okay, and then let's just get one log. Okay, and then summary test. If I run this class, what do we have here? Okay, so this is the full summary printout. And of particular interest for us is this one, the value of our T stat and the value of our critical values, T critical. Okay, if you recall, class, from our previous discussion of the T distribution. So this is our T distribution. Okay, our T stat is 35.0963, and you have here the confidence intervals. Let's use the 5% confidence interval. So the critical value is negative 1.95. Okay. And our T stat is somewhere here, negative 35.07 approximately. So it's in the rejection region. Okay. Recall, class, this is the rejection region. Therefore, if our T stat lies here, then we reject the null hypothesis. Right? We reject the null hypothesis that our time series LAP-RET has a unit root. So this is what it's testing, unit root. So a unit root is similar to, it's one of the tests for stationarity. So if a time series has unit root, it means that it's not stationary. So the null hypothesis here is that, let me write here, the time series has a unit root. So once again, unit root, class, means, okay, if it has a unit root, it means it's not stationary. Has a unit root, ibig sabihin nun, not stationary. Okay? Now, the T stat is negative 35, and then the T critical is negative 1.95 here. Okay? So this means, class, that we reject this null hypothesis that our time series has a unit root. It does not have a unit root, therefore, it's stationary. So this is, and in fact, whether you look at it at the 1% confidence interval, significance level, or 10% significance level, okay, in any of these cases, we still reject the null hypothesis. Okay, so our time series can be considered as stationary. Okay, so any questions about that, class? Any questions about this, class? Testing for the stationarity of our data. Okay, chat please if we're clear so far. Good. All right. Then, class, what's next? What's next? So we have step 6A that tells us that in order to determine, remember what's the end goal in mind? Our end goal in mind is to create a model using ARIMA for the time series of interest. The time series of interest is our log ApoRet. That's our LAP-RET. Okay. So after testing whether our data is stationary or not, we were able to determine that it's stationary. Therefore, we can now proceed to making use of ARIMA. Now, how do we do this? How do we do this, class? So before, okay, before, class, we had to determine ARIMA through trial and error, making use of the ACF and the PACF function. Okay, ACF and the PACF plot. What's ACF? ACF is autocorrelation plot, and then PACF is partial autocorrelation function. Okay, how are these computed? Okay, so this is our LAP red. How do you compute or how do you plot the ACF? But just for us to appreciate what's happening here, ACF. Okay, ACF lists, okay, so this is time 0, 1, 2, 3, 4, 5, etc. So we would like to know the correlation between 0 and log 1. Okay, and then 0 times 0, not the value 0, the time series, okay, the regular time series, which is LAP rep. Okay, so the question is, what's the correlation between LAP rep and LAP rep T minus 1? So this is time T, this is log 1. So how do we, well, it's very easy to compute for the correlation because you're just getting the correlation between this time series, right? Okay, assuming class this is the last. This time series, this is the log of AP rep, and it's log 1. So log 1 means this value will go here. This value will go here. This value will go here, etc. So you now have this log 1. Log 1 values plus, and then you get the correlation between this one and the log 1. Whatever correlation you get there, class, that will be your correlation at log 1. Then same thing, class, for correlation at log 2. So log 2 is 1, 2. So this will now go here. Okay. Right? This will go here. This will go here. So there will be two logs. So I now get the correlation between the original data and my log 2. Okay, so that's my log 2. You now compute for the correlation, and then you plot here the correlation. Whatever the correlation is, you plot here. So the autocorrelation will now get is a function that gives us the correlation between your original and your log 1 and your log 2 and then your log 3. So that's your PACF. On the other hand, your PACF is this one. Your PACF is you will regress your LAP PREP at time t. So you have a certain constant, let's say B sub 0 plus B sub 1 times LAP ret P minus 1. Okay, so you're using log 1 to explain your original data series, your LAP ret. Okay, and you also add plus B2 LAP ret T minus 2, and then etc. T minus 3. Now the values that you're going to get here, B1, B2, will now be your partial autocorrelation values. Okay, so you'll also have your partial autocorrelation plot. Okay, whatever values of T1, B1, B2, B3, etc. So that's how you compute for your ACF and your PACF. Okay, now what's the use of that, class? The ACF and the PACF allows us to determine what is the AR model, what is the ARIMA model for our time series. Okay, so this is where we are. We plot the ACF and the PACF to determine the potential AR and MA. Okay. Now, of course, there's a better way, quote unquote, better in the sense that mas shorten yung process natin. Okay. By using the identify the best fit model using the auto.arima function. In other words, class, we can skip the sixth method, the sixth method. We can still plot the ACF and the PACF anyway. That's very easy. But kasi it will be now be parang trial and error method na, no? Kung hahanapin natin in determining what's the model using the ACF and PACF. So let me share with you this one, class. Okay, so kindly look at this. Open this, Control C, and then I'll explain to you how we determine what ARIMA model is a time series using the PACF and the ACF. Okay, there are several class. There are several resources about this. So I'm just giving you one. So this one, interpreting ACF and the PACF plots, autocorrelation plots and the partial autocorrelation plots. So let's take a look at this. All right. So this one class, identifying AR, MA, and ARMA terms with ACF and PACF plots. So notice this class, our ACF is geometrically declining. Okay, so ibig sabihin nito class, the correlation between our time series and its log 1 is very high at around 0.80 something plus. Yung sa log 2 niya mataas pa rin. Log 3 mataas pa rin. Log 4 mataas pa rin. And then it decays slowly, no? Geometrically declining. Okay, this is geometrically declining. However, in the partial autocorrelation function, in the regression model class, okay, si log 1 significant, si log 2 significant also. Anything above this blue line class, ito, are significant correlations. Okay? So log 1 significant, log 2 significant, the rest is not significant. Okay, if your ACF and PACF plots look like this, then it says here a gradual geometrically declining, okay? ACF to, and at PACF that is significant for only a few lags. Okay, so tingnan nyo to, no? Significant spike and then wala na. Significant spike at lag 1, lag 2, and then no more. So if your PACF looks like this and your ACF looks like this, then most probably this is an AR process. In fact, this could be an AR2 process kasi dalawa yung significant dito. Pwede, no? So magiging trial and error to. Susubukan mo natin AR1 process ba to? So mag-create tayo ng AR1 process. Tapos AR2 process ba to? Mag-create tayo ng AR2 process. Or still, we can also check if this is an MA1 process or an MA2 process. So you create several models and then i-compare natin AIC. Okay? So ganun ka-tedious class tong model na to, making use of the ACF and the PACF in order to determine kung anong klaseng model ba to. On the other hand, ito naman MA process, tignan nyo class, opposite lang siya. If your PACF shows a geometrically declining PACF and your ACF has significant spikes and then cut na, okay, in just some few lags, then this is a candidate for an MA process. And so this is how before we did we did some checks, no? We did some trial and error modeling. Kasi i-model namin to, kung assuming AR1 process to, ito yung magiging result. Then compute for the AIC, yung AKIK. And then ito naman, tinan naman natin kung MA, titingnan pa pala kung AR2 process to, no? Diba? Or MA or MA1, MA1 or MA2, and then compare class. Compare kung ano ba yung pinakamaliit na AIC doon, AKIK. No? Tapos pag ARMA naman class, pag ganito, pag parehong geometrically decay siya, candidate yan for ARMA process. Parehong may AR at saka may MA component. Okay? Tapos meron pa ditong seasonal. Pag seasonal naman, makikita natin class na may mga significant spikes at regular intervals. Kunyari ito, siguro parang every quarter, no? Okay? Every 4 months, kunyari, no? This one, significant. Ganon din si PACF. Okay? So, pag ganyan class, ito naman seasonal MA. No, negative yung mga natin, yung mga significant na correlations. Ito naman positive. Okay, so it's quite a challenge class to determine. Okay? So buti na lang class, meron tayong shortcut. But before we do that, let's go back to our here class and then okay. Let's plot class. Have I given this to you class? Ito? Did I give this one ACF and the PACF?
Hindi pa po.
Okay, no, sige. Dalawa ibigay ko. All right, let's see. let's see this. Let's plot the autocorrelation and the partial autocorrelation function. Okay? So just take note, class, yung autocorrelation function. Ano lang yan? Correlation lang. It's a measure of correlation between your original time series and yung original, class, yung log uprep sa atin, ha? That's what I meant by original. And the log 1. Original and log 2. Original and log 3. That's what you get for the ACF. Yung partial naman, ire-regress nyo. Magre-regress kayo. Ito sa hanapin natin yung values ng parameters, yung B1, B2, B3. B1 will be your correlation for log 1, correlation for log 2, etc. Okay, so if we run this class, nag-partition tayo two rows, one row, two column na lang. One row, two columns. Balikan natin 1, 2. One row, two columns, and then i-run natin to, class. Ayan, okay? Kasi kanina 2, 1, two rows, one column. All right, so take a look at this, class. So ito yung ano natin, yung autocorrelation function at saka partial autocorrelation function. All right. Nawawala yung ano nawawala yung hindi ko makasya yung ano. Anyway, ito lang titinan ko, no? So from the looks of it, class, significant at log 1, significant at log 7, log 8. Significant siya, class, kasi beyond the beyond the blue dotted lines. So possibly AR process to, no? Okay? Or ARIMA, kasi ito hindi naman exponential decay to, hindi naman slow geometric decline tong tong ACF. Okay? So actually, class, ang hirap, no? Mahirap kung sa terminology natin, ma-eyeball, no? Mahirap malaman talaga ano ba to, AR1. So before, class, talagang masyadong madugo kasi yung trial and error. AR1 muna, subukan ko muna yung pinakasimple muna. Siguro AR2, tapos AR5 ba? Tapos susubukan din MA, tapos ARMA, combination na ng AR at saka MA. So that makes it difficult. So if we, how about this? Ito mas madali to, class, no? Using the TSM package, kaya nga sabi ko sa inyo, it's important that we load this package na to, and then just use the AC function. Autocorrelation ni log uprep. Yung maximum log, class, you're just getting the log ng 1, 2, 3, 4. Pwedeng 12 yan, pwedeng 16, pwedeng 18. Ano naman yan it's arbitrary, no? So I'm just using 24. But you can use 12 or 16 or 18 or 24, no? Pag may seasonality, mas maganda kung hanggang siguro 36 para makita natin yung kung daily yung data natin, 36. So that means 36 yung seasonality natin, no? Okay, so take a look at this, class, and we can see here that side by side siya, no? Tapos pareho lang naman ng kanina, no? You can see here some significant, si PACF significant at log 1, ganun din si ACF. Okay, so ano ba to? ARMA ba to? ARMA process ba to? Okay? Or meron pa ako dito isa. Okay, hindi na, no? All right. So as I said here, looking at the ACF and the PACF, it's not really that easy to determine. The ACF and the PACF, they're just their guides there, no? So meron tayong mga general guidelines, but mahirap din i-ano yun, class. So enter auto.arima. Auto.arima, class, allows us, kayo na lang magsulat, ha? I'll not share that with you para masulat nyo rin. No? Auto.arima function allows us to, si computer na, si R9 mag-generate ng iba't ibang possible na models, no? Okay, and let's remove first trace is equal to true. Okay, what will happen if I remove this? Yan lang. Okay, log APRAT. Take note, class, be careful, ha? Ito yung minomodel natin. Baka magkamali kayo, AP yung lagay nyo, no? Alright, if we run this, class, Okay, there. Automatically sasabihin sa atin kung ano yung best model for this. So here we're told that this is an ARIMA100. Explain ko in a while, no? All right? And then with, ito yung coefficient natin. Ito yung AR1 coefficient. Ito yung mean. Okay, and then we have here some values ng AIC, corrected AIC, and then the Bayesian information criterion. All right. Let me control Z. Ibalik ko class yung kanina, no? Ano tong trace is equal to true? Okay, this is convenient and good because it will give us kung ano yung trial and error na ginawa ni forecast package. So if I run this, okay, tingnan nyo class, no? Nag-trial and error siya based on the ACF. Ito yung sinubukan niya. ARIMA 202 ba? ARIMA 00, may ARIMA 10 siya, etc. No? Okay, with non-zero mean, with zero mean. So you can notice here na may mga models na non-zero mean at saka zero mean. Ibig sabihin ng zero mean, yung model natin walang average, walang mean. All right. So let's just backtrack a bit, no? Okay. May I ask you, class, if you were able to generate this, yung auto.arima model natin? 6B, ito? Yeah, ito. Ito, Adi. Yeah, okay. Sige, so tell me, class, paki-chat if you were able to generate this output. I'll wait for your feedback. If you have questions, like yung si Adi nag-question, good. Thank you, Adi. So please don't be ashamed to ask questions. Let's wait for the others. Dalawa pa lang yung nagbibigay ng feedback. Okay. Since step 6A. Okay, 6A class is, yeah, we plot the ACF and the PACF, and then manually we determine kung ano yung ARIMA model. 6B class is you still plot the ACF and the PACF, just for discussion purposes, no? But you're not going to make use of that to determine the ARIMA model class. Yun ang difference. Si 6A, if pina-plot natin si ACF and PACF in order to manually or by trial and error determine kung ano yung ARIMA process. Si 6B naman, i-plot pa rin natin ACF and PACF and just a guideline, no? Parang guess lang. Possibly AR process, possibly MA process, but nothing definite. Okay? We are only able to finally tell or determine kung ano yung model natin by the auto.arima function. Okay, so take a look at this class, no? So thank you for your feedback, class. Okay, so ito yung mga models na trinay ni auto.arima. Okay. So we have this ARIMA 202. Now, question. Ano ibig sabihin itong 0 dito, class? Remember yung ARIMA natin? Yung ARIMA natin, ang general format niya is P, D, Q. Where P is the order of your AR process, Q is the order of your MA process, and D is what's your D, class? Anyone, please? Paki-unmute na lang. Ano ibig sabihin ng D natin, class? Oh, Mark, ano ibig sabihin ng D? Okay, thank you, Adi. Yeah, differencing. Now, ang question ko, bakit 0 lahat, no? Itong nominated na model niya, bakit 0 lahat? What's the answer, class? Why 0? Which means, wala nang differencing. Bakit kaya walang differencing? Di ba, dinifference natin to, class? Di ba, linog natin, tapos dinifference natin? Now, why are we being told here that 0 means no differencing? Anybody, please? Why? Yeah, thank you. Yeah, thank you, Adi. Yeah. So Adi, yan yung answer yung sinabi ni Adi, ano. Now take note, ano ba yung minomodel natin? Ang minomodel natin, class, is log AP breadth. Okay? Ito yung minomodel natin, class, ha? We're not modeling AP. Okay? We are modeling the log of the apple returns. And we plotted this, and we know that this is already stationary, di ba? Constant mean and constant variance na to eh. Even by testing whether we're using the ADF test or the that DF test or the KPSS test, whatever test class, lumalabas talaga na stationary na. So itong zero na to class pertains to your log apple ret. Na? So ang sinasabi nito, huwag nyo nang i-difference. Hindi na kailangan i-difference si time series na to. Okay, so contextual to class, ha? Contextual to. I'll discuss this in a minute more. Okay. Now, sino dito class yung nasabi dito using approximations muna, no? Kasi kung talagang i-compute niya nga naman to na talagang very precisely, then tatagal. So dito sabi niya approximations muna. And which is the best model here, class, based on approximations? These are your AICs. Okay, akaiki yan, no? Yung sabi naman natin na the better model is the one with where the akaiki is the least, no? So dito class, the least among this one is ito. Kasi negative to, di ba? Negative to. So ang least ito yung pinakamalaking negative. Ito 'yon. So it turns out here that based on this options, ang pinakamaganda is ARIMA1 with non-zero mean. Ibig sabihin, may mean to, no? Okay, kumbaga parang may intercept. Okay, so let me delete these drawings. Okay, and go down here. All right, tapos finalize niya dito. So now, remodel niya class without the approximations. Tingnan nyo, initially 11,695 yung AIC. Ngayon, 11,693 na lang, no? Without the approximations na kasi approximate lang to. And the best model is AR100. Okay? Ito yung P natin. Okay? Order ng 1 for the AR process, 0 order for the MA process. Okay? With non-zero mean. And in fact, ito yung coefficients class. So this is the coefficient for your AR1, and this is the coefficient for the mean. All right, so let's run this class. So ano yung model natin? Okay, so we can get the names of model 1. So i-run nyo na lang to. Names ng model 1. Okay, so what's inside model 1? So andyan yung coefficient, log likelihood. So this is a list, no? Iba-iba, andyan yung AICC. Okay, andyan yung mga residuals. Andito yung mga predicted values. Andyan yung number of observations. Okay, and let's just get the coefficient. Kasi naka-round off dito yung ano no? Kanina, parang 4 decimal places lang. So let's get the coefficients. All right, so ito yung value, ito yung ano natin class, no? AR1 component. Okay, so let's now write the, mag-ano lang tayo, mag-LaTeX tayo. Okay, so our model is yung LAP ret natin at time t. Okay, so this is a time series, no? Is equal to, so this is our intercept. Control C, this is our mean. And then this is the AR1 component. Control C, Control V. Okay, now recall class yung AR1 component is a regression based on past values niya. So i-multiply natin to kay Control C, Control V. Okay, however, ito yung order 1 kasi, no? T minus 1. So this is the past value, log 1. And then plus, ano natin si epsilon, error term, epsilon underscore t. Okay. All right, take a look now at our model. Okay, so our time series, yan, sub t, no, is equal to, this is our mean minus AR1 class log 1 yan, di ba? LAP rep T minus 1. Okay? T minus 1. And then plus a residual. Kasi hindi naman magiging, sabi natin, di ba, hindi naman magiging equal tong actual value na to at saka yung predicted value nito. Kung may discrepancy, then it's accounted for this one. Unless class, again, back to what we learned before, pwede natin itong lagyan ng hat dito, hat, tapos tanggalin natin itong epsilon sub t. So you know that, class. All right, so I'll pause for a while and give you a few seconds, class, to write your problem. And when you're done, class, paki-chat. No? Okay, so medyo ano tayo sa oras, ha? Saan makahabol tayo dun sa ano? If you're done, class, kindly chat kagad so that I know. Kasi medyo may mga i-determine pa tayo. Okay, waiting for the others. Diba? Lucky questions? Okay, good. Thank you. All right. So I hope you're able to follow, no, class? Okay, so ganito gawin natin, ha. Ngayon, what if we were modeling si AP, si Apple? Okay, suppose the problem was model Apple. Model the AP stock adjusted prices. Okay? All right, Control Alt I. So, kung ito ay model natin, class, di ba, sabi natin, i-check natin kung stationary. And we know that this is not stationary. Okay? So, if we don't convert it or transform it into a stationary data set, and then i-ano lang natin, let's see what happens to your ACF and PACF. Okay? Ito na ako. Ito, no? Okay, just to review, class, yung plot natin ni AP, remember this, class? Hindi siya stationary, di ba? So sabi natin, dapat mo convert mo na into stationary. Eh, hindi nyo ginawa, class. So nag-ano na kayo, dumiretso na kayo sa autocorrelation at saka partial autocorrelation. Now hindi, class, sorry. Ito dapat AP, ano? Mali. AP to, AP. What will now happen if you plot the autocorrelation and the partial autocorrelation function of your AP? Okay. Oh, paano mo model yung class, no? This is a slow decay. Wala dun sa mga model natin class na magsasabi sa atin kung anong klase model to. Although si PACF, and tingnan nyo si PACF, no? 1, no? 1. Ano ibig sabihin yan, class? Ano ibig sabihin yan? Perfect correlation to, perfect collinearity, perfect correlation, di ba 1? With its past log 1 value. Okay, so may problem tayo dito, no? We will not be able to model yung AP natin. Buti na lang, class, meron tayong di ba? Meron tayong auto.arima, no? So let's model AP. Control C. Copy nyo, class, yung mod natin ng Okay. Saan na ako? Here. Ano ko nga to? Okay, so I'll call this mod 0 na lang. Mod 0. Mod 0 to. So I'm going to use also auto.arima, but this time for AP. Okay. So pwede rin palang kahit na hindi stationary, pwedeng gamitin si auto.arima. Pwede, class. Okay. Si auto.arima will tell us anong model yan. Okay, so i-run natin to. Trace is equal to true. All right. So ito yung mga ano niya. Ito yung mga suggested na models niya. And take note, class, no? Tingnan nyo, may mga 1 dito. So ibig sabihin nito, class, kailangan i-difference natin si AP. No? Kailangan i-difference natin si AP. And ang lumalabas dito, class, is ito. ARIMA 011. Okay? Tapos ito daw yung coefficient ni ARIMA. Yan, no? MA siya, class. Control C, Control V. MA na negative 0.4. Okay, so that will be the model for the AP data. The AP data class. MA siya, MA1. Okay, we'll write that model in a while, but paki-ano nga class, paki-chat naman class kung you were able to follow. I might be going too fast, class, no? But please tell me if I need to repeat a particular part. Ginawa lang natin dito, class. Ginamit natin si auto.arima kay AP, which is not a stationary data series. And ang lumabas na date na ARIMA 011. Okay. Kindly chat please if you were able to get that answer. Lumabas dito ARIMA 011. Okay, good. How about the others, please? So ang 1 dito, class, ibig sabihin difference dapat, hindi pwedeng si AP lang as is. Kailangan i-difference to. About the others, kindly chat please kasi medyo nag-ano rin tayo sa time. May mga kailangan pa ako i-discuss. Okay, good, thank you. Now, would it have given us the same answer? What if, class, copy ko na lang to dito, no? And then I'll make this 0, 0. Tapos, di ba may DAP na tayo, class? DAP, class, is your difference apple object. So what will happen if we instead model yung DAP? Okay, which would have been the same for this one kasi difference data set to, no? Okay, so i-run ko lang to, class. And take note. Ayun, nawala yung dito sa gitna, no? Sa 0, walang differencing. And ang final model niya is this one. Ayun, class, no? ARIMA 001. So it's still an MA. And then, yung coefficient na to are the same as yung kanina sa ARIMA na 011 natin. Okay? So it's exactly the same class. Kasi dito, dinifference natin. Ito naman, sabi niya, i-difference muna tapos minodel niya. Alright? So I hope that's clear, class. Isulat lang natin yung model ng for our exercise, class. So, once again, ilagay ko lang dito, class, yung mod 0. mod 0, and then coef. Okay, so ito yung ano niya, di ba? Ito yung magla-latex ako. And copy this. Ito muna. Ito yung mean, control V. Ito yung MA natin. Control C, control V. Okay. So ano yung model natin dito? Okay, take note, this is the difference of a apple. Difference ng apple to class, ha? And this is a time series sub P. Alright? So ito yung apple, yung prices natin to, ha? Hindi ito yung returns, ha? And then the difference natin, ang sabi ng model. So it's equal to the mean plus, okay? So this is MA, plus natin yung, okay, usually minus, pwedeng plus or minus, but usually we use the minus, epsilon underscore T, and then minus, may kulang ako dito, minus, and then minus, times, epsilon, error term underscore, T minus 1. Okay, take a look at our model class. Yeah. So our difference apple stock is the mean minus your error term minus MA1 class. MA1. Log 1 of the residuals. Pag MA2 yan class, dalawa. May epsilon T minus 1 ka at saka epsilon T minus 2. Okay? All right, so I'll give you a few seconds to work on that. And kindly chat, please, if you were if you're able to get it. Okay, good, thank you. Waiting for the others. Kailangan nyo to class sa ano sa case number 2 kasi ipapamodel sa inyo yung ARIMA, and then it should not stop there kasi inagagawin natin ngayon, no? We're going to check if okay na tong model na to. So how do you do that? Once again, check the residuals. Magda-diagnostic sign ito. Okay? So let's go there now. Okay, ito nasagot na natin, ano? Okay, ito class. You can check if ito yung discrete returns, no? Yung log returns natin L. I leave you class 2, your mod 1.1 to check kung anong difference ng ano ng kung if we were modeling the discrete returns and the apple returns, the log returns. You'll find out class na hindi masyado nagkakalayo, no? So hindi masyado nagkakalayo, konting difference lang sa coefficients. Okay? So I'll leave that to you class to find out. It's also an ARIMA 100 process din to. Ito class si ano to si discrete returns. Okay? So not so much difference between the discrete returns and the log returns. All right. So before we can, okay, i-share ko na tong ano, no? Huli na to class yung step 8, no? Huli na to. Kasi bago tayo mag-forecast, kailangan i-check muna natin yung model natin. Magda-diagnostics tayo here. All right, so let me share with you this code chunks. Kakasya ba? Sana kumasya. Let me see. Control C. Ayan, good. Okay. Paki-copy lahat, class. Okay. Let's now go to our diagnostics. Okay. So, di ba, let's check yung model 1 natin, class. Remember, ang model 1 natin, class, mod 1. Okay, names ng mod 1. Okay, maraming laman to, di ba? Yan, makukuha ko coefficient dyan, number of observations, yung log likelihood, AIC, AICC, etc. So, you know how to get those values, class. Ang focus natin, class, titingnan natin yung residuals natin. Okay? Kasi di ba, dapat yung residuals natin, class, just like, kasi parang regression din ng AR, no? Ang ARIMA. So dapat yung ano natin, residuals natin should not be heteroskedastic, no? Okay, so dapat yung correlation, yung autocorrelation mga residuals, there should be no autocorrelation. And kung sa ano, class, kung sa cross-sectional data, hindi na natin titingnan yan. Dito kailangan natin tingnan yan. We have to look at it here. Kasi, class, remember ang time series, diba? Yung arrangement ng data niyan, it's really structured so that there's a tendency for the residuals to have correlation. And we don't want that, no? So, na-share ko na to sa inyo, no? So let's take a look again at the ACF and the PACF. Ito na lang ipa-plot ko, class. Okay? This one. So you can see here, oh, may mga significant pa rin, class. Dun sa mga later lags, lag 6, may mga significant pa rin. So medyo may autocorrelation yung residuals natin. Okay? Kasi take note, ano bang kinukuha natin na autocorrelation function. Okay? Autocorrelation function ng residuals natin. Okay? So clear, class? So clearly, class, dito may autocorrelation. Yung residuals natin, kunyari, residuals at time 0 is correlated with the residual at lag 6. So that's not good, class, because that indicates that there's autocorrelation. And ito, I share this with you, class. This is also a good way to plot this using from ggplot, meron tayong GG, ACF, and GGP ACF. So it also records yung ACF and PACF, pero mas kita natin. No? So makikita natin dito sa lag 6, o significant yung correlation. Okay? Although sa later lags, halos wala na. Pero yung ACF natin, class, ganoon din. So pareho yung behavior ng natin ng ACF at saka PACF. Merong significant autocorrelation yung mga residuals natin. Alright, then we can test, dapat nasa uli na to, no? Pero ito na muna, no? We can use the Shapiro wheel test in order to test whether our residuals are normally distributed. So itest natin to. The null hypothesis here is that the residuals are normally distributed. And ito, we reject yung normality. But then again, class, just like in cross-sectional multiple linear regression, pag malaki naman yung sample size natin, pwede na natin medyo disengage yung sarili natin dito. But the residuals are not normally distributed. And this one is a very good plot, class. No? Check residuals model 1 kasi it puts into one, okay? Pinagsama niya yung mga plots dito. Tingnan natin. Ayan, tingnan nyo, class, yung plot na to. Andito yung residuals, okay? This is the residuals of your ARIMA100 with non-zero mean. Ito yung residuals ng model natin, ba? And you can see here, may mga volatility clustering. Okay? Maganda sana, class, kung white noise lang to, which means dapat yung residuals natin, dapat walang lumalabas, class, sa sorry, medyo hindi maganda yung ko. Okay? Okay, let me, ito. Dapat ganito yung residuals natin, class. Walang nag-volatility clustering sa taas, sa baba, sa taas, sa baba. Ito. Okay, this indicates class volatility clustering, which means that the ARIMA model was not able to capture this. Okay. So, aside from that, class, ano pa yung pinaplot sa atin dito? Aside from the residuals, class, plinot din yung ACF, class, no? Nakita na natin to kanina, and also the normality. So, kita nga natin na hindi siya peak siya, no? hindi normally distributed. All right. Okay. Now, kanina, yung plot lang ang tinignan natin, ano? Okay? Ito lang yung chinek natin. Yung autocorrelation. Now, we can do a box dot test to see if may autocorrelation nga. So let's check this. I gave this to you already, no? So this one will check kung ring residuals natin may serial correlations, yung autocorrelation to, no? So if I run this, okay. The null hypothesis is that there is no autocorrelation. There is no autocorrelation between the residuals and its log. But here, class, we have p-value, a very low p-value, which means we reject the null hypothesis of no serial correlation. Merong serial correlation. Okay? So, ibig sabihin yung ARIMA process natin, hindi na-capture yun. Also, this one, class. Another test I gave you. So, you have to load yung Norge test, no? Tingnan nyo to, ha? Ito test natin. This is an arch test. Autoregressive conditional heteroscedasticity. It tests if our residuals are heteroscedastic. So anong object natin? Yung residuals ng model 1 natin. Okay, so dalawang methods dito, box at saka Lagrange multiplier. And then alpha natin, define natin at 0.05. That's our significance level. Log.max natin 2 na lang, no? So if I run this, okay, what does this tell us? Ang null hypothesis natin dito is that the residuals are homoscedastic. P-value is less than 0.05. So we reject the null hypothesis that our residuals are homoscedastic, heteroscedastic siya. Okay. And lastly, class, this one, it's almost time. Ito, class. Arch test. Okay. Run natin to. All right. So ano din yung importante dito, class? Sana nawala. Here, arch test, class. Same thing, no? Same thing. Our null hypothesis is that our residuals are homoscedastic. We reject the null hypothesis. Okay? Yung arch test natin, ang sinasabi niya, there is the presence of arch. Ano yung arch? Autoregressive conditional heteroscedasticity. So our residuals are heteroscedastic. So yung model 1 natin, yung ARIMA model 1 natin was not sufficient. Therefore, class, ano yung next step? Since it did not stand the test, no? Yeah, correct. So ang answer sa question ni Fe, what if, especially in heteroscedasticity, no? Kung wala, class, then pupunta na tayo sa next, no? Magga-gauge na tayo. In order to address that, there's another way we have to do that. So magsa-step 2 na tayo, yung gauge. Generalized autoregressive conditional heteroscedasticity. So anong gagawin natin, class? Magpo-post ako ng video ng gauge model, class. So you have to watch that, okay? And then you have to see how we can now model yung log apple returns natin making use of gauge. All right? So yun na, class. Yun na yung case number 2 nyo. Model some time series. Ipapost ko, class, yung requirements using ARIMA gauge. Okay? ARIMA, tapos gauge. So you have to go through the ARIMA process, test the residuals. Usually naman talagang yung residuals hindi heteroscedastic, hindi homoscedastic. And then you go to the next, which is gauge modeling. Generalized autoregressive conditional heteroscedasticity. So arch na dinagdagan ng G, generalized. All right, so let me stop recording now.